EX67. Let's talk about, again, tensor product, this time basis of tensor product as a free R module. So the most trivial example would be you have field and then vector space over that field, and then you take the tensor product of the vector field of the vector space, then it's again vector space, and basis is given by the tensor, the elementary tensors of the basis of each vector space. Okay, this is a very similar statement, but argument is more general here. If we have, so again, this is following a lecture notes by Keith Konar on the internet. So let's say if f and f prime are free are modules with basis EI and fj respectively, then show that EI tensor fj, I in I, j in j form a basis for the free R module f tensor f prime. Okay, let's say the first part of the exercise. The second part, closely related, deals with the situation that one of those R module is free if M is an R module. No more condition on it. The F is a free R module. With basis EI, then every element of M tensor with F as our module has a unique representation. In the form, in the following form. So and in the component of f, I take the basis element EI, and in the component of M, I just take arbitrary element of it, but I claim all but finitely many and I are 0, which means this is a finite sum. So basically what is important here is the uniqueness, right? The existence is more or less trivial. You just by the R linearity move the R coefficient of EI to the left hand side into the M component. Okay, so let's prove solution. Firstly, for that part, so what's the difficulty? Basically, so let's just check by definition. Basically, you have to use again the universal property. Basically, the idea is that you could define freely a map on EI Fj for a given I and j, and then this bilinear map is defined uniquely. Okay. So how do you define that? And this is the idea, okay? And so let's start with the proof. And then we see what we need. So basically we just want to check if you have expression EIFJ, right? Clearly EIFJ, if EIFJ, let's denote this coefficient, Cij equals 0. So this is obviously f tensor product with f prime. Then we claim all the Cij equals 0. How to show that? How do we prove this? So without loss of generality, we prove C, let's say so when we're talking about this free R modules, we are basically not requiring it is finite at all, whatever, right? We're just saying that we're taking, let's say, I mean I cannot write say 0 0 because Ig are not necessarily countable infinity, something like that. Let's just say let's prove say I0 J0 equals 0 for some I0 in R fixed, J0 in J fixed. Okay, so what do we do? I'm going to come back to construct a linear map, a bilinear map. I'm saying that I could define this bilinear map very freely, but once I finish defining it, everything is fixed. So I'm going to define it to be 0. Let me say first, define to be 1 if I equals I0 and J equals J0. For all other possibilities 0. So basically I'm kind of just emphasizing on this EI0 FJ0, right? Check this is bilinear. So this is bilinear, R bilinear. Basically you extend the definition by R bilinearity and then you claim you have defined it on the whole set of product with f prime. And then this B implies there exists a map from f tensor f prime to R sending, let's say sending whatever EI, tensor fj and Cij. Ij is mapped to what? It's mapped to only this Ci0 J0 because all the other terms are killed. It's called this F. And in particular, if this is 0, then this is mapped to F0, which should be 0, but it is also Ci0 J0. So this implies Ci0 J0 equals 0. By the generality, this implies that actually Cij equals 0 for any ij expressed in this expression. And so we have proved this indeed gives you a linear independence. Okay, so we have proved are linearly independent, and that's all, because its generating set is trivial. We've discussed that a lot. So let's go to the second. The second part of the exercise asks you to prove that if M is just an R module, but F is free R module, let's say with generating set EI, then an element could be expressed in a certain form. Firstly, this is the expression, so let's say Ci, this is free R module, so CIEI, sorry, CJJ, right? So this is IJ, because the CJ is in R, can move it left hand side, MICJ, EJ, and this is again inside M. So basically an element could be written into the form just some MI and then wait. Let's just keep one index. Let me write it this way. Here is I, but I move this J outside, so it's kind of like this. For fixed I, there is J. And then this is also for fixed J, some Mi prime, some Mj prime. Let's see. This is in M, and then tensor EJ. Okay, so this is okay. So the point is to show the uniqueness. Summarize what I discussed. We can write every tensor in M, tensor R is F, as a sum. Elementary tensors of the form Mi tensor EI. So we have surjective linear map. Let's call it F. From the direct sum of R modulo M to this tensor product. Mapping this Mi to Mi Mi tensor is EI, and to do the summation. So notice that we are taking from here, so finitely many Mi are non-zero, which means most, and so this is finite sum, well defined. We want to create inverse of F. So we start with, again, by universal property, start with this bilinear map. So Mi so let's see, whatever M, whatever, because this is the basis, I'm mapping it to inside M, so I'm just take MRI. Wait. Yeah, this is it. So recall this I here is the indexing set of EI. So let's recall our goal is to prove this. And so this is bilinear. Let's just call this G. Let's call this G tilde. So G tilde is bilinear. So it induces a map G from the tensor product to this direct sum of M. Right. And then let's check. F compose G. equals identity, and G compose F equals identity. Once you have done this, we have proved as our module there is isomorphism. And this map is by our construction. Like this. And then the uniqueness of coordinates which means if you have any element here, map it to G of X, element of here, and then its coordinates unique. And this implies the sum representation is unique. What does it mean? Let's say if x equals x mi tensor ei equals some mi prime tensor ei with just mi prime inside m. I don't assume they are the same. I want to show they are the same, right? That's the uniqueness. Then apply G, and we have mi equals mi prime, right? And so we have proved they are the same. Prove the uniqueness. The interesting thing is just look at this. This is not what we claim to prove, but we use this to prove the uniqueness. This is more or less telling you that how to think of elements in the tensor product of M tensor with f over R. Element is uniquely determined by the coefficient of the M component, not the coefficient, the corresponding component on M for each basis element ei. This is uniquely determined by this part, right? I just collect them, and the uniqueness is telling that, okay, in this way, this is really like free. I'm not saying this is a free R module, but the freeness of the F over translate back to kind of the freeness of freeness on each component. Okay. Let's put a remark. For ring, so for this I left you to check. So for a ring R containing S element, so S tensor of R with Rx. So this is a free R module. Right, this is our module by our just proved exercise of a unique expression of the form Si tensor x to the power, because x to the power inform a basis as our module for Rx. So R bigger or equal than 0. And so any element could be expressed in this way, and so this is also isomorphic to Sx, and the map is just map this Si tensor Xi to Six